Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. In this November lecture series, we are going to discuss about some basic topics in biocontrol system. First, we are going to discuss about physiological modeling, and thus we will discuss about mathematical modeling of systems here. Okay, first of all, the control systems can be represented with a set of mathematical equations. It is known as mathematical model. These models are useful for analysis and design of control systems. We know that very well, and we have some mathematical models which are frequently used in biocontrol system, like a differential equation model, transfer function model, and state space model. Okay, here in this mathematical model, we use a set of equations. Usually in control systems, it is differential equations here that represents the dynamics of systems. In practice, the complexity of system requires some assumptions in determination model. Here, how do we obtain these equations? And here the physical law of the process is established, and we have some examples over here, like mechanical systems, Newton's laws; electrical systems, we use Kirchhoff's laws. And here the main element in equation is transfer function. What is this transfer function? Why do we need that? In control system, we use some kind of mathematical modeling to give correct accuracy in practical applications. We use some assumptions. Before that, we saw electrical equations and mechanical equations. In that, we follow Newton's law and Kirchhoff's law. Same thing, transfer function, it plays a main role in control system. What is a transfer function? Any idea? Okay, transfer function model is an S-domain mathematical model of control system. Here, the transfer function of a linear time invariant system, it is called LTI system, is defined as the ratio of Laplace transform of output and Laplace transform of input by assuming all the initial conditions are 0 here. Here our input is x of s, s is your system input, and we have y of s. The output transfer function is y of s by x of s. It means the transfer function of an linear time invariant system is the ratio of Laplace transform of output and Laplace transform of input by assuming all the initial conditions are 0. Here, see the mechanical system output. See here, it shows a scheme of an active vehicle suspension system. See here. See, in this mechanical system, we have the elements, mechanical elements M1, M2, and also we have R1 and R2. See, vehicle and active suspension point, and wheel and tire, and also we consider rough terrain too. Here, and this right side picture, we have damper, coil spring, and here in this mechanical system, for this wheel, for this mechanical system's wheel, we chose the elements like M1, M2. Also we have omega, K1, K2, B1, B2, and we have force F, R1, R2, and also we use the term rough terrain. By using this kind of basic elements, we can represent a mechanical system basically. See, mechanical systems mainly consist of three main elements, namely mass, dashpot, and spring. If a force is applied to a translational mechanical system, then it is opposed by opposing forces due to mass, elasticity, and friction of the system. Hence, the applied force and the opposing forces are in opposite directions, and the algebraic sum of the forces acting on the system is 0 here. See, here the mass, See the diagram. Mass, here the formula is Fm directly proportional to alpha, that is A. Here Fm equal to ma, it is equal to m multiplied with d square x by dt square, and F equal to Fm, it is equal to m d square x by dt square. Why this differential equations? Normally, while representing systems, we use differential equations. Here, F is applied force and Fm is the opposing force due to mass, m is mass, a is acceleration, and x is displacement. See here, while coming into spring part, it is represented as K in this diagram. Remember that F directly proportional to X. Here Fk equal to Kx, F equal to Fk, it is equal to Kx, where F is the applied force, Fk is the opposing force due to elasticity of the spring, K is spring constant, and X is our displacement. And next one is dash part. See this symbol, Fb directly proportional to V. Here Fb equal to Bv, it is equal to B multiplied with dx by dt. F equal to Fb, it is equal to B multiplied with dx by dt. Here F is the applied force, Fk is the opposing force due to friction of dash part, and B is spring constant, frictional coefficient, and V is velocity, and X is our displacement. Here, the transfer function of the mechanical translation system is given in this figure. In this figure, we can represent f of t equal to fk plus fm plus fb. Okay, x of s by f of s, it is equal to 1 by ms square plus bs plus k. See the electrical system, how it is represented over here. Here we have resistance, inductance, and capacitance. It is represented in Vi in time domain. Here V R of t is equal to I R of t multiplied with R, and V in Vi means voltage current characteristics. In S domain it is V R of s, it is equal to I R of s into R. And while coming into induction part, in this inductance, VL of t, it is equal to L multiplied with dIL of t by dt. And in S domain it is VL of s equal to SLIL of s. While coming into capacitance part, Vc of t, it is equal to 1 by C integral IC of t dt. In S domain, Vc of s, it is equal to 1 by Cs multiplied with IC of s. Here R is your resistance, here L is your inductance, and C is your capacitance. Here the transfer function g of s, it is equal to E naught of s by Ei of s of the RLC network. See the example RLC network. Here we have inductance L, resistance R, and capacitance C. Here your input is Ei and the output is E naught for an electrical system. By applying the Kirchhoff's voltage law, here the summation V is equal to 0, because we have to make all the states are 0 over here. Here the formula is Ei of t is minus L di by dt minus Ri minus 1 by C integral I of dt, it is equal to 0 for this circuit. Here finally we will get 1 by C integral I dt, it is equal to E naught over here. Thank you.